Hello, I would like to welcome you to lecture 24 of 2FH3. We'll discuss in this lecture the concept of inductors and inductances, and this is taken from chapter 8 of the book of Sadiku, page 362 to 366. In our previous lectures on magnetostatics, we discussed the concept of magnetic field H. We said that current will create magnetic field, and the magnetic field is related to the magnetic flux density through mu for the case of a linear medium, of course. So if you consider here a loop like this one, we have here a number of turns, and there is a current I going through them. So this current I will create inside this loop a magnetic field H, and it will create a magnetic flux density vector B. If you want to get the flux going through these turns, the way we define flux, and we talked about this before in many lectures, that the flux is simply the integral of B. So I can simply say that psi is simply the integral over the cross section of B dot ds. So here I'm trying to get the total flux going through the cross section of each one of these turns. But now we need to generalize this concept a little bit to see how many times that this flux encloses the current, because we have the current I, but this current I has n loops. So if you try to draw one closed circle of this flux here, so maybe actually I can continue this one, complete this one here. So you could see that this flux line here encloses the current n times. So this gives rise to the concept of flux linkage, that not only we are looking forward to the flux through the cross section, but to something else we call lambda, which is a flux linkage. How many times does this flux encloses the current? How many multiples of times it encloses the current? And here is equal to n. So for the ideal case where the total flux is going through this coil here, it does not leak, then all these turns will have the same psi, and the total flux is simply is equal to integral B dot ds. And now we can simply say that lambda is equal to n multiplied by psi. Now one word of warning, of course, psi, if B is uniform, and this is an assumption we can make in some cases, that in the cross section B is uniform, then the integral of B dot ds, as we have done before in many examples, can be written as B multiplied by the area, if B is constant. And this is what we had here, lambda is equal to n, number of times the flux encloses the current, multiplied by Bs. And now, but we know that the B is coming from the integral from Ampere's law, and from H, and it's proportional to Ni, to the multiple of Ni, because if we have only one turn, we have certain magnetic field. But if we have two turns and they are very closely spaced, the magnetic field will be doubled. If we have three turns, the field will be tripled, and so on. Then the magnetic field itself, the strength of the magnetic field or the strength of the magnetic flux density, is proportional to n. Now in order to calculate the flux linkage, you multiply by another n. So you have to keep in mind that the flux linkage is always proportional to the n squared for a structure like this one, and for a linear case it's also linearly proportional to the current. The concept of inductance really depends on the concept of flux linkage, and this is coming really from the work of Faraday and how time varying fields create voltages. So here, if we already were able to calculate the flux linkage for a certain circuit, for a certain coil, for a certain conductor, then we know that lambda is linearly proportional to the current. Then this constant of proportionality is what we call the self-inductance, L. So L is by definition the self-linkage flux that we have divided by the current. This is one way of defining the self-inductance. You start by calculating from the current, you calculate H, from H you calculate B, and from B you get the flux psi, and then you multiply psi n by how many times it encloses the current to get the flux linkage, and then you divide the flux linkage as I'm doing here by the current, and this will give you L. This will give you the inductance. This is one way of calculating it. Another way that we'll be addressing later is through the definition of magnetic energy. We know that the magnetic energy stored in a certain inductance is 1/2 Li squared. So the inductance can by definition be taken as the ratio between 2 multiplied by the magnetic energy divided by the current squared. And I will show you in the following lecture how to calculate the magnetic energy in a certain structure using the values of B and H. So we'll be doing that. So once you calculate this to be certain integral, certain volume integral, once you calculate this volume integral, you divide it by I squared until multiplied by 2, and this will give you the value of L. This is pretty much it for the definition of the inductance. Now, what will follow a number of examples to show you how to apply this definition. The very standard way or the very systematic way of calculating the inductance, assume the current, get H, from H get B, from B get the total flux psi, multiply by the number of times it linked through the current to get the flux linkage, divide by the current to get the inductance. So now we have a toroid example. We have a toroid. It's the current here. We have a number of turns. The current here is one loop. It's coming out from the page. Here is going into the page. So these are all turns. Okay, and it has if you take a cross section here, if you take a look through this cross section, we assume it has a square, not square, rectangular cross section here on both sides. So it has a height of h and it has a width of w. The inner radius for this toroid is ρ1, the outer radius is ρ2, and the middle radius is ρ0, which is really half ρ1 plus ρ2. So we addressed before the example of a toroid. We said that because of the symmetry, the magnetic field will be in the phi direction, and it will only depend on ρ. And we applied Ampere's law. We took an Amperian path, if you recall that. It was like a circle, and then we applied Ampere's law. The integral of h dot dl is equal to the current enclosed. And by doing that, we were able to get this expression for h. We found out that h is flowing in the phi direction. H will be in the phi direction, so all the flux lines are in the phi direction. And it's equal to Ni over 2 by ρ. So it decays with ρ. So the more ρ increases, the lower the value of the magnetic flux, the magnetic field will become. And there is no magnetic field outside the toroid because the total current enclosed is 0. You have current coming out from the surface, and you have current cancelling it coming into the surface. So if you take any closed surface here, this will give you 0. Now, B is simply equal to H multiplied by mu. So multiply this number by mu. And now if you get the total flux, this flux is flowing in the phi direction. Then you have to integrate over the cross section. And the cross section here is a cross section like this one. So it has a width of W. Actually, it's d ρ if I take a small element. And maybe I should be showing that. If I take a small surface element here, this surface element has a width of d ρ, and it has a height as well of h. So this has to be very clear. Or of course I can take a small element of it that's going to be dz. So the element in the cross section, if I draw it in the side here, it will look something like this. I'm trying to draw it for you. It will be something like this. An element in the cross section. This one here is dz, and this one here is d ρ. So we multiply this by the flux, by the flux density, and this will give us a differential flux element. And then what you do, you have to integrate this flux, which is multiplied by the differential surface element in the phi direction, d ρ dz. This is B here, you multiply by the S, which is d ρ dz, and then you integrate to get the total flux. You integrate from ρ1 up to ρ2, and you integrate over the height from 0 up to h, and this is what we have here. There is nothing here that's a function of z, so the integral relative to z will give you h. This is d ρ, and you are integrating 1 over ρ d ρ, then you get ln ρ, both upper limit minus the lower limit. So this is a flux going through the cross section of the toroid. This flux, which is going through this one here, how many times does it enclose the current? You can see here it doesn't go through one loop, it goes through one loop, a second loop, third loop, fourth loop, and so on. So it encloses the current n times. So whatever psi we calculated here, we have to multiply again by another n to get the flux linkage. So the flux linkage here is simply equal to n multiplied by psi. This is why you get n squared here. And from the definition of the inductance is by definition the flux linkage divided by the current, so it's lambda over I, and then when you do that here, I will disappear. You get this expression for the inductance in henries. Now, if the cross section is thin, if it's a pretty thin toroid, then the field is almost uniform and it's equal to its value in the center. So from Ampere's law, we can take h phi to be the same and take its value to be equal to the value at rho naught, where rho naught is the middle radius, and this is what we have here. So the value, the expression that we have here for phi is that we simply calculated h at the center for the center rho, which is rho equal to rho naught, and we say this will be pretty much the same in the cross section because it's thin. Then if h does not depend on the cross section, then b is simply equal to mu h, and then psi in that case is equal to b multiplied by s. We don't have to do a surface integral as we did here. And this is what's happening here. We multiplied by mu to get b, and then we multiplied by the area. What is the area here? The area is this part. This is the area. It is simply equal to h, the height h, multiplied by w, and w here is nothing but rho 2 minus rho 1, the width of the cross section. So this will work fine as an approximation if the toroid is a thin toroid. Let's take a look at one more example. We have here a solenoid, a pretty long and thin solenoid, and it has n turns. There is a current I flowing through it. It has a radius of a. It has a length of d. Now, for such a solenoid, if we apply Ampere's law, of course, the way we calculated the magnetic field for solenoid before is through an integral. But for something like this one, if we are only interested in the magnetic field in the center of the solenoid, what we can do, we can simply take an integration contour like this. So I'm trying to draw it for you. I will take my Ampere's law at this contour. So I will apply Ampere's law to this contour. This is going through the center, and this going out, and then this is moving outside, and this going back again. Okay, so I'm going to apply h dot dl over this contour. So we apply Ampere's law that the integral of h dot dl is equal to the current enclosed, equal to I enclosed. Now notice one thing. We know from the solenoid or from our experience with this structure, that if you take a closed surface, there can't be any magnetic field outside, because the current enters the surface at one point and then leaves it on the other side. So the field outside here is zero. The field here, the field is in the axial direction, the z direction. So h dot dl here will give you 0. H dot dl here will give you 0. H dot dl here will give you 0 because there is no field here. There is only h dot dl along this center line, and then we can simply take this as d. So this would be h is constant here. So this will give you hd. So this Ampere's law will give you hd is equal to I enclosed, and I enclosed is equal to n multiplied by I, because we are enclosing the current n times. If you take a look here, we are enclosing the current in this loop n times. It penetrates the surface and surrounded by this contour n times. So if from that you can get this expression that's used here, that the magnetic field will be in the z direction, the axial direction, it is equal to Ni divided by d. And if we assume that it is uniform inside, because the solenoid is pretty long, then the corresponding B is nothing but Bz will be equal to mu multiplied by Hz. This of course applies in all cases. And once we have B, we can simply multiply by the area in order to get the total flux psi. So this is what we have here. So multiply this by mu to get B, and then B by the area to get the flux. Now, this flux, which is going through this loop, and it will look something like this one. It's going through this way, maybe depending on the direction of the current, of course. How many times does it link this current? How many times does it include this current? It actually includes this current n times, and n is the number of turns. This is why we take here the flux linkage is equal to n multiplied by psi. So you multiply this also by n, so this will give you this expression. So the inductance by definition is equal to lambda divided by the current in the loop, or the current in the circuit is lambda over I. So it gives you here mu n squared A over D. This is the expression for the inductance of the solenoid. So to try an example with some numbers, let's try to calculate the inductance of a toroid with 200 turns. The cross section is square, so W is equal to H is equal to 1 centimeters. Its inner radius is 1.5 centimeters, and they will take the material of this toroid to be because it's, remember, we have these turns. They are both on some core. So the core here is, we assume it is ferromagnetic. It has pretty high permittivity. It's 400, and we want to calculate the inductance here in this case. So this is the cross section of the toroid. It is 1 centimeter by 1 centimeter. The current is, of course, I'm not showing you the turns here, but this is the inner radius 1.5. The outer radius will be 2.5. The middle radius will be 2. So I will use the approximate expression we derived earlier for the toroid with the thin cross section. So mu n squared A over 2 pi rho naught. N is given number of turns 200. We know that mu, the material of which the toroid is made, is ferromagnetic. It has mu r equal to 400, so mu is equal to 400 mu naught. The area, this cross section area, is 1 centimeter by 1 centimeter. So this is 10 to the minus 4 meters squared. The middle radius, we know the inner radius 1.5, the outer radius will be 2.5, then the inner radius rho naught is 2 centimeters. Now, if you go back and you substitute all this in this expression, we are able to get the value of the inductance. So, putting all this together, you can see this is mu r, this is mu naught, this is n squared, this is the area, divided by 2 pi rho naught. Rho naught is simply equal to 2 centimeters, 2 to the minus, multiplied by 10 to the minus 2. 4 pi will cancel with 4 pi. This is 10 to the power 4 will cancel 10 to the power minus 4. So you have here 4 multiplied by 4 coming from here, so this will give you 16, and this will go up at 10 to the numerator as 10 to the power 2. Then the total power will be 10 to the minus 5. So and the answer will be 16 10 to the minus 5 multiplied by 10 to the power 2. This after you simplify everything, and this will give you 16 millihenry. Of course, this is an approximate one. If you try to use the exact expression of this one, I believe that you'll get 16.3 millihenry. So the difference between them is minimal, but I would suggest you try also to apply the exact expression, the one that does not assume thin solenoid. Thin toroid here in this case. Sorry. One last example, which I think is very important, is to calculate the self-inductance of a thick conductor of radius A and permeability mu that carries a uniform current I. And you'll see why this example is a little bit different. So let's now take a look at this one. We have a thick conductor, current is flowing uniformly in that conductor. It has a radius of A and it has permeability of mu. Usually, unless mentioned, take mu as mu naught. So here we have the conductor. This is the conductor here. Current is flowing uniformly out from the bridge. I'm not showing it at every point, just at this point here. We did calculate before the value of and we know from actually from previous work that we did that the magnetic field will be in the phi direction, and it will only depend on rho. And we applied, if you apply Ampere's law and take an Amperian path that looks like this one, looks like a circle, then you will get that the value of H increases. And we did discuss this earlier. Inside the conductor, it increases as the radius increases from 0 up to A. So the value of H that we calculated earlier, and you can check previous lectures, is I rho over 2 pi A squared A phi. Now in order to get the corresponding flux, so B will be also in the phi direction, you simply multiply by mu. Now here we don't have turns. Here we have a continuous current. And we have to see what is the percentage of this continuous current that the flux is enclosing. Before, the percentage was actually multiple, because when you have number of turns, you are not actually, the flux lines are not enclosing fractions of the current, they are enclosing multiples of the current. 1, 2, or 3, or 4, or 5, depending on the number of turns. Here, if I take a small contour like this one, and then I try to determine the cross section, of course I have to do an integration in the cross section here, and this cross section, an element in the cross section here will be d rho dz in the phi direction. Such an element, such an element of flux which is shown here, b d rho dz, enclose how much current? What is the percentage of the current encloses? This whole cross section has a current of I. This one here encloses a fraction of that current. The fraction enclosed, of course, is given by the ratio of the two areas, because the current is uniform. So it's equal to pi rho squared over pi A squared. So in order to get the flux linkage, you have to multiply this d psi by pi rho squared over pi A squared in order to get the flux linkage. And here you have to understand that this flux line, if I draw one of them, if I try to draw one of these flux lines here, this flux line here, okay? This flux line is going this way. This flux line encloses a fraction of the current. A fraction, not multiple as in the case of coil. This has to be very clear. Fraction of the current. And this one here is simply pi rho squared over pi A squared. Once you understand that, the rest is easy. The flux linkage, as you can see here, this is the flux linkage. It is simply given by d psi by I enclosed over the total I. And I said this will be the ratio of the two areas because the current is uniform. It's pi rho squared over pi A squared. Now, if you multiply these two, this will give you, from the previous slide, this will give you rho to the power cube, the numerator, and it will give you a to the power 4 in denominator. If you want to get the total flux linkage, you have to integrate to get the over dl to get over the whole cross section. See how much flux is linked throughout the whole cross section. So you integrate z from 0 up to L, the length of this conductor. You integrate rho from 0 up to A. The integral of rho cubed from 0 up to A will give you rho to the power 4 divided by 4. So you put A to the power 4, so we'll cancel. This 2 becomes 8. The integral of Z will give you L. So if you put all this together, you get that the flux linkage is linearly proportional to the current in the conductor, and is equal to mu I L over 8 pi. So if you divide now both sides by I to get the inductance, so the inductance of a thick conductor is equal to mu I over 8 pi. And it's independent of its radius, of the radius of the conductor. It's mu I over 8 pi. And we'll be using this later in other examples.